Today, I will be discussing Hardy-Weinberg equilibrium and selection. We will look at a fictitious species that I have named the Arctic shrimp. The color of these shrimp depends on a single autosomal gene on the A locus. A homozygous dominant shrimp will have the blue phenotype. A heterozygous shrimp will have the purple phenotype, and a homozygous recessive shrimp will have the red phenotype. In this population of shrimp, we have 55 blue, 30 purple, and 15 red shrimp for a total of 100. The first step in determining how this population is affected by selection is to calculate the frequencies of the alleles. To find the frequency of the A allele, you multiply 2 times the number of big A individuals plus the number of big A little a individuals and divide that by 2 times the total population. Doing this, I calculated a frequency of 70% for the big A allele in this population. To find the frequency of the little a allele, you simply have to subtract the frequency of the big A allele from 1. Doing so, I calculated a little a frequency of 30% for this population. Now we will verify that the population is in Hardy-Weinberg equilibrium. The Hardy-Weinberg equilibrium states that the allele and genotypic frequencies will arrive at equilibrium after one generation of random mating, so long as the population follows these assumptions. There must be an infinitely large population, which there is, however we are only observing 100 out of this infinite population. There must be random mating, no selection, no mutation, and no migration, all of which are satisfied by this population. If the population is at equilibrium, then the frequencies of the genotypes can be determined by the equation listed here, where P is the frequency of the big A allele and Q is the frequency of the little a allele. When the P and Q values found earlier are plugged in, we see that our population of shrimp satisfies the equation for Hardy-Weinberg equilibrium. Let's now assume that the phenotype of the shrimp influences the likelihood that they will be able to find a mate. For example, let's say that these shrimp are preyed upon by a new species of fish just introduced to the Arctic waters, which I will call the Arctic shrimp eater. The blue shrimp has an advantage because its color blends into the water, and therefore the shrimp eater can never find and eat blue shrimp. The purple and red shrimp, however, do not blend into the water and therefore get eaten by the fish. We will say that 45% of the red shrimp are eaten by this fish before they have a chance to reproduce. 65% of the purple shrimp are eaten before reproducing, while all the blue shrimp are able to survive predation and reproduce thanks to their ability to blend in with the water in which they live. These values here are the fitness values for the shrimp based off the predation we just discussed. Now we can determine the frequencies of the genotype after selection has occurred. What I have here is a chart that displays the calculations for the frequencies of the genotypes after selection has occurred. We start by finding the initial frequencies, which is the number of individuals divided by the total population. Then the fitness values are listed, which we were given earlier. The values for the unadjusted survivors are found by multiplying the corresponding fitness values and initial frequencies. And finally, the frequency of the genotypes after selection is found by taking the corresponding unadjusted survivors value from above and dividing them by the average fitness. The average fitness is the sum of the products of multiplying each genotypic frequency by its fitness value. The calculated values are listed in the chart here. Also, the frequency of the big A allele and little a allele after selection are calculated here. Now, looking at a comparison of the original population and the population after selection, we can see that the blue phenotype increased, as indicated by the green arrow, and the purple and red phenotypes decreased, as indicated by the red arrows. This is an example of directional selection because we can clearly see that in this population, one allele was favored over the other. What this means is that if this type of selection continued, we would expect to see the frequency of the blue phenotype increasing while the frequencies of the purple and red shrimp decreases. Eventually, we could even see one of the genotypes completely disappear from the gene pool, and we would no longer see that color of shrimp in the population. Here are the external sources I used.